This is ELC111, Intro to Electricity, and this presentation is on RC, RL, and LC filters. Now, before we begin looking at filter circuits, I need to define impedance. Impedance, symbolized by the letter Z, is measured in ohms. Again, the unit symbol is the Greek letter omega, just like resistance. An impedance is defined as being the opposition to alternating current. Impedance is a combination of resistance and reactance. And you recall that reactance is the frequency-dependent opposition to a sinusoidal alternating current, as seen by an inductor. Inductive reactance, symbolized with X sub L. Mathematically, X sub L equals 2 pi FL. And the reactance of a capacitor, capacitive reactance, symbolized with X sub C, which mathematically equals 1 over 2 pi FC. So anytime we have an alternating current source, we don't think of just resistance, we have to think about impedance. Now, RC, RL, and LC filters, of course, are comprised with resistors, capacitors, and inductors. So this figure 1 shows us the plots of X sub C and X sub L reactance as a function of frequency. And looking at the curve that for X sub C, note that X sub C is large at low frequencies and is small at high frequencies. Inductive reactance, X sub L, is small at low frequencies and is high at high frequencies. So we use capacitors and inductors to construct our filter circuits. And it's the relationship of the components, either resistors and capacitors, resistors and inductors, or inductors and capacitors, that determine if the circuit will function as a low pass, high pass, band pass, or band stop filter. So let's take a look at a low pass filter implemented with an RC combination. So referring to the circuit of figure 2, excuse me, we see a resistor identified as RF. This is the resistor that makes up the filter circuit, and a capacitor CF. And the operation of this circuit is that at high frequencies, X sub C is small, so all the high frequencies are passed to ground through the capacitor. So at high frequencies, this capacitor, again referring to figure 1, is a low opposition to current, or a low impedance at high frequencies, so all the current goes to ground through the capacitor. Now at low frequencies, the opposition to current of the capacitor is extremely high, so the only path for current is through RF to the output. So at low frequencies, the output is maximum, and at high frequencies, of course, the output, V out, is smaller. Now, again, when discussing these circuits, our point of concern is the cutoff frequency. And this is the frequency where the signal is considered to be filtered out. And again, as we talked about in the previous presentation, the cutoff frequency is the point where the output power drops to 1/2 of the maximum output power. The output voltage drops to 70.7% of the maximum output voltage. And this is the -3 dB point. And we look at the graph and we can see that at -3 dB, the output, this is the cutoff frequency right here, which is approximately 2 kHz. So for for the low pass filter circuit of figure 2, the cutoff frequency mathematically is 1/2 pi RC. So substituting in the values for R and C of 120 ohms and 0.68 microfarads, we calculate a cutoff frequency of 1.95 kHz. Now, the circuit of figure 4 shows us a high pass filter implemented with an RC combination. Again, at high frequencies, the capacitor X sub C is very small. So at high frequencies, we find nearly a short between V in and V out. So the output is maximum. Of course, at low frequencies, X sub C is very large, so we block current from flowing from V in to V out through the high impedance of the capacitor. As with all of our filter circuits, the cutoff frequency is the point where the signal is considered to be filtered out. This is the half power point and the point where the output voltage drops to 70.7% of the maximum. This is also the -3 dB point. So looking at our graph, -3 dB is somewhere around here. So the cutoff frequency will be right here, which again is approximately 2 kHz. Mathematically, the cutoff frequency of the high pass filter of figure 4 is 1/2 pi RC, which again gives us a cutoff frequency of 1.95 kHz. Now we see in the circuit of figure 6 a low pass filter that's implemented with an RL combination, an inductor and a resistor. Referring back to the plot of figure 1, we see that at high frequencies X sub L is very large. So high frequency AC energy is blocked from getting to V out by the high impedance of the inductor. And at low frequencies, X sub L is very small, so there's a low impedance path between V in and V out. So at low frequencies, the output is maximum. Again, with all of our filter circuits, we're concerned about the cutoff frequency. This is the point where the signal is considered to be filtered out. And this is the half power point and the point where the output voltage drops to 70.7% of the maximum. And this cutoff frequency is also the -3 dB point. So looking at the graph, we see that the -3 dB point is somewhere, again, around 2 kHz. Mathematically, the cutoff frequency of the circuit of figure 6 is R divided by 2 pi L. So substituting in our values for R and L, 1.2 k ohms and 100 millihenries, we calculate a cutoff frequency of 1.92 kHz. Now, the circuit of figure 8 shows us the implementation of a high-pass filter using an RL combination. Again, referring back to the plot of figure 1, at low frequencies, X of L is very small. So at low frequencies, we see a path for current, a low impedance path for current through the inductor to ground. And of course, the output is minimal because the majority of the voltage is dropped across RF, the filter resistor. And at high frequencies, the inductor is a very large opposition to current. No current flows through the inductor. The only path for current that we have is through RF in this direction. So the output is maximum at high frequencies. As with all of our filter circuits, the cutoff frequency is the point where the signal is considered to be filtered out. This is the half power point, the point where the output voltage drops to 70.7% of its maximum. This is also the negative 3 dB point. So for this filter circuit, the cutoff frequency, the negative 3 dB point, is right here. Again, it's approximately 2 kHz. Mathematically, the cutoff frequency for the circuit figure 8 is R divided by 2 pi L. Again, substituting in our known values for R and L, we calculate a cutoff frequency of 1.92 kHz. Now let's take a look at the operation or action involved or related to an LC circuit. So this circuit, as we see in figure 9, has a series combination of an inductor and a capacitor. Now, in any series circuit, the current through all components is the same, both in magnitude and time. So the current supplied by the source, V1, is the same as the current that flows through the inductor, is the same as the current that flows through the capacitor, again, both in magnitude and time. However, recall from our discussion of inductors and capacitors that there's a 90-degree phase difference between voltage and current in an inductor and a capacitor. That voltage leads current by 90 degrees in an inductor, and current leads voltage by 90 degrees in a capacitor. So referring to figure 10, we see here that, of course, the inductor voltage happens 90 degrees ahead of the current in the circuit. So there's a 90-degree phase difference between voltage and current in an inductor. And of course, with a capacitor, capacitor current leads capacity voltage by 90 degrees. So note that the capacitor voltage, VC, happens 90 degrees after current. Now, looking at this plot in figure 10, note that when the inductor is a positive maximum, the capacitor voltage is a negative maximum. And of course, when the capacitor is positive, the inductor voltage is negative. Now, it's somewhat difficult to illustrate, or it's easier to illustrate this phase difference between capacitor and inductor voltages using a vector diagram. Recall from figure 10 that the inductor voltage happens 90 degrees ahead of current. And again, in our series circuit, current is constant through everything, so we put current on our vector diagram as the reference point, which is here at 0 degrees. And since the inductor voltage leads current by 90 degrees, we place the inductor up here at positive 90 degrees. And since current leads voltage in a capacitor by 90 degrees, we plot the capacitor voltage on our vector diagram down here at negative 90 degrees. Now, when we think about the oppositions to current in the circuit of figure 10, the rules of vector math say that X sub L, inductive reactance, mathematically equals V sub L over I. And if we have V sub L at positive 90 degrees divided by I at negative degrees, then our X sub L has to be plotted here also at positive 90 degrees. And X sub C, capacitive reactance, equals VC divided by I. And again, if I take VC at negative 90 degrees divided by I at 0 degrees, I plot X sub C down here at negative 90 degrees. So looking at these vector diagrams, we see that X sub C and X sub L are opposite. And this is opposite with respect to time. And what this means is that when X sub L opposes current, X sub C is pushing current. And when X sub C opposes current, X sub L pushes current. Sort of like the push me, pull you creature from the Dr. Dolittle movie. So another term that you need to be familiar with is resonance. And again, we see a plot here of reactance, capacitive reactance, and inductive reactance. And X sub L, 2 pi FL, gives us this plot here, and X sub C, 1 over 2 pi FC, gives us this plot here. Now, these two functions, X sub C and X sub L, have to intersect at some point, as we see in figure 13. And the point where X sub L and X sub C intersect, the point where they are equal, is called the resonant frequency, symbolized with F sub R. And at resonance, X sub C and X sub L will cancel out, because remember, X sub L and X sub C oppose one another. So at resonance, if X sub L equals X sub C, I can substitute for X sub L 2 pi times F sub R times L, which would equal 1 over 2 pi times F sub R times C. We're simply setting X sub L and X sub C to be equal to one another. So if I rearrange this equation and solve for F sub R, I get that the resonant frequency is equal to 1 over 2 pi times the square root of L times C. So let's take a look at an LC combination used to implement a band pass filter. and we see this in the circuit of figure 14. So we have a series combination of C1 and L1 connected to this in between the source voltage V1 and V out, and of course we have to have a load resistor over here in order to have somewhere to drop the output voltage. Now the resonant frequency for the circuit of figure 14, 1 over 2 pi times the square root of LC, calculates to be 1.07 kHz. And the center frequency of this bandpass filter is equal to the resonant frequency of the LC combination. Now, referring to the Bode plot provided in figure 15, at the resonant frequency, X sub C and X sub L cancel. So the combination of C1 and L1 is essentially 0 ohms at resonance. So at resonance, all the current, or let me restate that, at resonance, V out is approximately equal to V1, because again, at resonance, these two components cancel out, and from here to here, at resonance, we have 0 ohms. Now, at frequencies below resonance, now X sub C is greater than X sub L, and we start blocking AC from passing to V out. At frequencies above FR, the resonant frequency, now X sub L is greater than X sub C, and the inductor blocks AC current from flowing to V out. So again, referring to the plot of figure 15, we see that at the resonant frequency, 1 kHz, the output is at its maximum because X sub C and X sub L cancel, and at frequencies below resonance, the X sub C is greater than X sub L, X sub C blocks AC. At frequencies above resonance, X sub L is greater than X sub C, and the inductor blocks current. Now I can also use this series LC combination to implement a band stop filter. And we see an example of a band stop filter in figure 16. So we have the series LC combination placed in parallel with the load resistor, in parallel with the output. We do have to have a series resistor R1 in the circuit between the source and the series LC combination. Now the resonant frequency of the circuit of figure 16, this says figure 13, figure 16, 1 over 2 pi times the square root of LC gives us a resonant frequency of 59.9 hertz. And again, for the band stop filter, the center frequency is equal to the resonant frequency. So looking at the Bode plot provided in figure 17, we see that at the center frequency, at the resonant frequency, again, X sub C and X sub L cancel, which means that from here to here, we have effectively 0 ohms of impedance. Therefore, all of this voltage V1 is dropped across R1, and of course the output approaches 0. And this is why R1 has to be in the circuit, because at the resonant frequency, since the L1C1 combination is 0 ohms, we have to have a component here in series with that LC combination, or else we would short V1 to ground. Excuse me. Now, at frequencies below resonance, X sub C is greater than X sub L. Now, this LC combination is not a short, and current finds an easier path, or there is a path for current to flow through RL, because again, X sub C is so large. So we see from the Bode plot in figure 17 that the output increases at frequencies below resonance. Now, at frequencies above resonance, X sub L now becomes greater than X sub C, but again, we find a large impedance here, so there's an easier path for current to flow through the load resistor, and of course we have a voltage developed, so V out increases at frequencies above resonance. So we've looked at, or in this presentation, we first of all defined impedance as the opposition to alternating current. It's a combination of resistance and reactance. Then we looked at implementing low and high pass filters with RC combinations. We looked at implementing low and high pass filters with RL combinations. We defined or described and discussed the operation of LC combinations, and we defined the term resonance, or the resonant frequency, and that is the point where inductive reactance and capacitive reactance are equal. And then we looked at using series LC combinations to implement band pass and band stop filters.